Today's lesson is on polynomial and rational inequalities. A polynomial inequality is any inequality that can be put into one of these forms. F of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0, where f of x is any polynomial. Here are two examples. X squared minus 2x plus 1 is less than 0. Notice that's a quadratic is less than 0, or x cubed plus 7x squared minus x minus 7 is less than 0. Notice that that is a higher order polynomial. Now there's two methods of solving polynomial inequalities that we're going to discuss today, and these same two methods will apply to rational inequalities as well. One method is the graphing test, and the other method is the sign test. I'm going to do a lot of the problems twice today, so you can see how to do it in one method or how to do it to the other. Now, at the end of the lesson, you can pick the one that you like better and do the homework and the problems on the test in that method. You don't have to do both methods. You just have to pick one and like it. So, for the graphing method, step 1 is to make one side equal to 0, like f of x is less than 0 or f of x is greater than 0. Step 2, let f of x be equal to the polynomial. So we're going to use the polynomial part as an f of x just for ease in evaluating and graphing. And then I want you to factor that polynomial. So for quadratic functions, I want you to only factor the x-intercepts, or we call them zeros, right? They're basically the same thing. And then also you need to graph the end behavior. Now earlier, in an earlier lesson, I asked you to do x-intercepts, y-intercepts, extra points. I wanted a beautiful graph. In this case, we are just using a very basic graph. Only x-intercepts and end behavior. It's going to be a very minimal graph, but it'll be enough to tell us where is above the x-axis and where is below the x-axis. Now for higher order polynomials, I also want you to graph the x-intercepts and zeros, but you need to remember that you have multiplicity when it's higher order. And then also you need to graph the end behavior. So basically the same, I just need to understand if it's higher order, you're going to have multiplicity. Step 3, mark the positive and negative y values on the graph, meaning where is above the x-axis versus where it is below the x-axis. The x-axis, or the 0, determines whether they're less than 0 or greater than 0. So then I want you to identify on the graph where the inequality is satisfied. Where does the less than or equal to or greater than or equal to satisfy the inequality? Number 4, the solution to the inequality is the x values, or we call that domain. Where the inequality is satisfied, don't forget you need to answer that in interval notation. Okay, so let's go back and go through the steps of the sign test method. Okay, step 1. So the steps for the sign test method are, number 1, make one side equal to 0, very similar to the graphing method. Step 2, let f of x be equal to the polynomial, very similar to the graphing method as well. Next, I need to find the boundary points. The boundary points are, in this case for polynomials, the x-intercepts. For rationals, they might be some other things, okay? Step 4 is to evaluate a point in each interval. So we're going to take our boundary points and put the boundary points on a number line. And when you put those boundary points on number lines, you find intervals of numbers, and we're going to evaluate a point in between each of those boundary points. Number 5, the solution to the inequality is the x values, or the domain, where the inequality is satisfied, again answered in interval notation. So we're first going to start with quadratic examples. Notice I have 4 different examples of the same polynomial. So in this particular case, our polynomial is f of x is equal to x plus 3, x minus 5. So I'm going to try to evaluate it and then find out where is f of x greater than 0 for the first one, where is f of x less than 0, where is f of x less than or equal to 0, and then where is f of x greater than or equal to 0. Okay, so I'm using the same function f of x. I'm going to find a few things for it. The zeros for this particular case is -3 and 5, or those are the x-intercepts as well. If I were to distribute it out, I would get x squared plus a whole bunch of other stuff. That x squared, when I distributed that out, tells me that I have a degree of 2, a leading coefficient 1, which means my end behavior is up and up. So graphing, very minimal graphing here. Just graph the x-intercepts and the end behavior gets me a quadratic graph. Again, this is not the best graph. It's just good enough to get us what we need, okay? Our next step says to mark the positive and negative y values on the graph. So looking at the graph, anything that's above the x-axis, the x-axis is right here, anything above it is going to be a positive value, and anything below it is going to get me a negative value. So I'm going to go ahead and mark those right on that graph just to remind myself what's above the x-axis and what's below the x-axis. Then I want to decide where is my graph satisfied. So in my first problem, I am looking at where is f of x greater than 0. Well, what's greater than 0? Positive things, right? So the positive part of my graph is right here and right here. So that is where the inequality is satisfied. So the solution to the inequality is the x values are the domain where the inequality is satisfied. We know it's satisfied where we have shaded. Those are the positive regions. The domain of those positive regions would be -infinity up until -3, union 5 to infinity. So the question now is, do I get to include these endpoints? And these endpoints right here are the x-intercepts, are the 0 values. So my question to you is, do I get to include the 0? Well, if you look at the inequality is less than, strictly less than. Anything that's strictly less than or strictly greater than does not include the endpoints. So because it does not include the endpoints, it would have a parentheses. If the problem was less than or equal to or greater than or equal to, then I would include the endpoints. And if you include the endpoints, you would get a bracket. So because it's not included, I'm going to use parentheses on these. Okay, let's look at the next one. Okay, where is my graph less than 0? Where is the graph less than 0? Well, in this case, less than 0 is negative, so that's below the x-axis. So my less than 0 spot would be down there in the green shaded. So where is my function less than 0? Well, I want you to give me the x values that give me values less than 0. So the x values start from -3 and go to 5. Do I get to include my endpoints? No, because it's strictly less than. On to the next problem. Where is f of x less than 0? Again, less than 0. That's the green shaded region that we talked about. But in this case, it's not just less than 0, it's also less than or equal to 0. So it's the same region, -3 to 5, but this time it's brackets. And on our last problem, we have where is the function greater than or equal to 0? Greater than or equal to 0, that's the yellow section that is above the x-axis, but in this case I get to include the endpoints, so my solution would be -infinity to -3, bracket, union bracket 5 to infinity. So that's all of the solutions for those. Let's do that same problem again, but this time using the sign test method. So the sign test method starts very similar. One side is already equal to 0, yay. I have a function f of x is equal to the polynomial. I just use f of x notation so that for the graphing method I could graph it, and for the sign test method I can evaluate. The f of x notation is just a little bit easier to solve, and then I can just focus in on where is f of x greater than 0. where is f of x less than 0? And so on and so forth. I know that seems like a little bit of extra work, but it really is helpful to have it in that notation, okay? So step 3 says find the boundary points, which are the x-intercepts. So my x-intercepts, or my zeros, are -3 and 5. So I'm going to go ahead and put -3 and 5 on a number line. Notice this isn't a xy plane, it's just a plain number line. Step 4 says evaluate a point in each interval. So I need you to understand that there are several intervals here. We have an interval right here, then you've got another one right here, and then you've got another one right here. The 2 boundary points breaks the line up into 3 segments, okay? So what I want to do is I want to decide which of those segments is positive, which of those segments is negative, and the way I can do that is I can just evaluate a point. This part gets a little tedious. So if I have f of, I need something in this blue section. So I'm going to pick something that's less than -3. I'm going to go ahead and plug in -4. So I'm going to go ahead and plug in -4 into the function f of x and evaluate it. So I'm getting -1 times -9, which is +9. Because it's +9 and the boundary points are the 0 points, they're the x-intercepts, that means everything in that blue interval will also then be positive. If 9 is positive, for one spot in that interval, the whole thing is positive, because the only part where it changes from positive to negative is at boundary points. Next, I'm going to try the interval in the middle here. So I have f of some number between -3 and 5. I'm pretty cheap. I almost always go for 0. If 0's in the interval, I like to try that one because 0 makes my arithmetic a little easier. So here I have +3 times -5, which is -15. Now, because it's in between the 2 boundary points, every number in between that will also then be negative. And then we have one more in the green section. So I need to pick something to the right of 5, so I'll pick 6. I need you to understand that you could pick 7 or 8 or 10. Just because I'm picking one number in this video doesn't mean you couldn't pick a different number. If you're interested, go ahead and try a different number and find out if it also is positive in the positive sections or negative in the negative sections. Okay, so that I found was a little tedious. I think it's probably a little faster just to graph it, but some students might like the sign test better. So now I'm going to go back and try to answer these. Where is my inequality satisfied? So the first one is f of x is greater than 0. What is greater than 0? Well, that's positive things, right? So my answer will be anything that's positive, so the domain of those. So I'm going to start at -infinity, go up to -3, union 5 is where the next positive part is, to infinity. Now the question is, do I get to include the zeros? Notice there's zeros on my number line. Well, in this case, I don't get to include them because it's strictly greater than. How about the next one? Where is it less than 0? Well, less than 0, that would be negative. So that starts at -3 and ends at 5, no including. The next one is, where is f of x less than or equal to? So it's still less than, so we're still talking negative. But in this case, it's not just negative, it's also negative and include the zeros. So that means I use brackets to include the zeros. And then the next one is, where is f of x greater than or equal to 0? So that's all the positive sections. So we have 2 of those positive sections. So I have start -infinity to -3. Include my endpoint this time because it's or equal to. Union bracket 5 to infinity. Notice that the solutions are the same when we found the graphing method or the sign test method. You do not need to do both. I really just want you to do one, but in this video I really need to show you both so that you can get the gist of both and pick your favorite.